Hello, everyone, and welcome to VSA Online. Really great to see you all joining. So I have a pleasure today to introduce Parikshit Ram from IBM Research in USA. So today the topic is associative memories. So not very, frequently appearing topic in our context, but you definitely all can make your own links uh, to associative memory. So Parikshit, please, the floor is yours.
Uh, thank you, Evgeny, for inviting us to speak at this venue. And again, thank you all, everybody for attending. Um, so the specific work that I'm going to cover today is dense associative memories through the lens of random features. But before I get into it, I mean, this is based on a paper that we had in NeurIPS in 2024. If you want to see the paper, the QR code on the top right will take you there. And this is with my collaborators, Ben Hoover and Polo Chow from Georgia Tech, and Hendrik Stovelt and Dmitry Krotov from IBM Research. And now, full disclosure, I'm going to talk about dense associative memories, but I am not going to talk about it either from the usual statistical physics side of things or some neuro-inspired learning side of things. I I am more like I have a more machine learning background, so I like to think of it from a machine learning perspective. And what I think of associative memories is a specific model. It's a model that maps a d-dimensional vector to another d-dimensional vector. But it has a very specific structure in that it's parameterized with some number of d-dimensional vectors, which are known as memories. So the model is parameterized by memories, and associated with this, connected to this model is what's known as an energy function, which consists of a similarity between the input to the model and some memory, some kind of a nonlinear activation, and some monotonic function. So this is uh, how I like to think about as the energy function. So then how does the model make predictions? It makes predictions by kind of doing an energy descent using the energy gradient. So the forward pass through this model is essentially a step uh, down the energy gradient. So that's how I view associative memories from a lens, like as a machine learning person. I think of it as a model with a very specific structure, which is very different from other structures that are commonly used, like feed-forward structures and all, which don't really have interpretations of what the model parameters are, or have any interpretation of what the inference is doing, what the forward pass is doing. Now, this energy function, of course, defines this model dynamics where a particular input uh, changes as proportional to the gradient of the energy. And this energy needs to have certain properties. You want it to be differentiable everywhere and bounded from below. Then it's what's often called the Lyapunov energy, which gives us guarantees that this dynamics will have fixed points, and under some conditions, these fixed points will actually be one of the memories that I have as parameters of my model. So that these are certain desirable properties of the energy function. And the energy of any state, you can like with in like in like using the Boltzmann distribution, like energy of any state is inversely related to the probability of the state. And so when you're doing this forward pass or inference with the energy descent, we are effectively doing we are maximizing the likelihood. And you can see the dynamics as like the input as being the initial state that seeds the energy descent, and then we take a bunch of gradient steps until we reach some kind of a fixed point as visualized on the figure on the right. Like we have the feature space on the x-axis and the energy on the y-axis. And we want to, starting from an initial seed, we want to get to one of the fixed points of this energy, and that will be the final output of the model. This is kind of how I like to think about associative memories as a model. And more memories, as you add more memories to your model, you can have more local minima. We are visualizing this in this video as we are adding more memories, the red dots. You can see that the energy landscape visualized by this vector field is gets more and more local minima. And as we add more memories, we usually get more local minima, but up to a point. There's a limitation there. And usually more memories imply more parameters, but if they do create more local minima, that gives us a more expressive model. Um, Now, this number of local minimas that we are always talking about is related to a concept of memory capacity. Like it's the number of memories that can form local minima of the energy. That's what's known as the as the memory capacity. And the memory capacity is is very much dependent on this nonlinear activation f function that I brought up earlier. And if this f function is just a quadratic function, then it has been shown that the memory capacity is bounded by the dimensionality of the memories themselves, which is d. So like that's the maximum memory capacity O of D that we can have. And this is what's known as the classical Hopfield network or classical associative memories regime. More recently, like in 2016, more like faster growing nonlinear activations have been used. So you can use like a polynomial of degree greater than 2, which then has a capacity, which is again polynomial in D. And if you choose the nonlinear activation to be the exponential function, then you can show that you can have exponential memory capacity. So you can store exponentially many memories in your model and have a local minima around each of them. Um, Now, this exponential capacity can be shown to be enough to have any kind of universal approximation guarantees, but that also means that you have to store exponentially many memories, which has increased computational overhead, both in terms of storage and in terms of doing the forward path, the inference. Now, what are these associative memories useful for? So one way they're commonly used are as error correctors. So you can think of like a real image, like this image of a bird, as being a memory. And you can configure the system so that the model has low energy at this memory. Then if you provide an input to it, which is a corrupted version of the image, this will actually be something which has a high energy. And then as you perform the energy descent using the energy gradient, uh, ideally, as you traverse the energy landscape, you get to a fixed point which corresponds to the precise memory that you're trying to recover. So they are error correcting systems. Of course, there are limitations, and that's tied to this notion of capacity that I was previously talking about. And if you don't have enough capacity, if you pack in a lot of memories into this model, but the memory doesn't have enough capacity, then you can get what are often called spurious memories, where even if you perform the energy descent, you get to a local minima which does not correspond to any of the memories that you have originally stored, and you just have something that looks like nothing like what you put in, and you cannot recover the original memories. Um, um, Now, even though capacity is an important issue, it also is kind of tied to storage. So as I've been mentioned, like if you have the quadratic activation, it corresponds to the classical associative memories, which have only linear in D capacity. It would correspond to an energy function of this form. Now this energy function has a very favorable form, which allows us to simplify the energy function to look like uh, the energy of any state to be negative of V transpose TV, where this T is essentially a sum of the outer product of the memories themselves. So it's just a D by D matrix. And in that case, I don't really need to keep the individual memories around. I only need this T matrix. And once I create this T matrix, I can get rid of the original memories themselves. And what that allows us to do is it kind of disentangles the number of memories from the number of model parameters needed to store them. So if I had just m memories in d dimensions, naively I would have to store m times d parameters, but with this specific energy function, we can simplify it and have to only store d squared. Uh, and so that is one advantage of this energy function, which can have low capacity. Now, in contrast, if we look at this, what's known as the log sum exp energy or the LSE energy, which makes use of the exponential uh, activation. Sorry. So sorry, I saw a question in the chat. Should I address it now, or should I kind of
We can. I think we can take it by the end of your
okay.
talk. So we collect all the questions online.
Okay, yeah, sorry. I think something popped up on Zoom and I got distracted. I apologize. Um, um, as I was saying, if we look at the log sum x energy, which utilizes this exponential activation, naively, we would need to store all memories explicitly. So we get higher capacity, but the computational overhead of storing all the memories also goes up. So in this paper, we actually want to address that specific issue, that we want to somehow keep the capacity without having to store all the memories. And we want to understand how that's possible and when that's possible. So to get there, we make a connection. So we realize that the energy function as written here can be also seen as a kernel sum. So if you're familiar with kernel machines, the whole big literature of kernel machines, and they were extremely popular and powerful models before deep learning took off. If we have a specific kernel K, which is written as the combination of the similarity function and the nonlinear activation, then the energy function is effectively the negative uh, of a monotonic transformation of the kernel sum. And kernel sums have been known to be expensive, and kernel machines, models based on kernel sums, usually require all training points to be kept around for inference, but more training points usually imply better expressivity. And so there are parallels between these kernel machines and dense associative memories. But one thing that like kernel machines were popular, but they were computationally very expensive. However, one thing that kind of made a big difference in the world of kernel machines was this paper by Ali Rahimi and Ben Recht in 2007, where they introduced these random Fourier features as a way to make kernel machines more scalable. And again, is a very well cited paper. This received the NeurIPS Test of Time Award in 2017. Um, now, what was the main tool that they used? So they used what's known as the Bachner's theorem, which states that if you have a kernel, which a shift invariant kernel, which is a kernel which only depends on the difference between the two inputs, then the shift invariant kernel has a one-to-one correspondence to a positive measure, shown by P over here. And the way that they're connected is that the kernel is exactly the Fourier transform of a positive measure. If that is in fact true, then it's a necessary and sufficient condition for the kernel to be positive definite. And the kernel and the positive definiteness of a kernel is critical in making the kernel machine work. So it's a very important property. So based on this observation, you can, like, given this observation, we can then see that if we look at this Fourier transform, um, it can be rewritten in this following form, which is an expectation over samples from that positive measure. This scalar product of two scalars, the exponential, like complex scalars, complex numbers, which is the exponentiation of the random dot product between the random vector omega and one of my inputs, and the conjugate, and the next complex number is the dot product of the random vector with z prime, the other input, uh, and the conjugate of that complex number. So essentially, it's an expectation using these random vectors omega, and you can of course approximate this expectation with just an empirical mean. The empirical mean just it requires us to take some number of samples from the positive measure, and then you just compute these quantities for each of the inputs, and then you can just take their average, and that can be shown to be a good approximation of the true expectation. And this empirical mean can be written as a dot product of a very specific featureization of the inputs. So this featureization phi is utilizing these random features to generate explicit representation of the inputs z and z prime. And this featureization is what's known as random features. Of course, this requires us to know what the specific positive measure is corresponding to each of the kernels. But for many of the popular kernels, this has been worked out, and this has been studied for over a decade at this point, and many various different very powerful random features have been developed for different kernels and for different applications. For our purposes, we are interested in seeing how we can utilize it to work with dense associative memories. And as I said, if I think of our random feature map as this function phi that maps d-dimensional vectors to a y-dimensional vectors, such that my combination of the nonlinear activation and the similarity function is approximately equal to the dot product of these random features, then what I can do is I can take my energy function and I can kind of do some simple mathematics and see that instead of saving all the memory patterns explicitly, I can instead save just an aggregate of the random feature representation of the memories, which would be this vector, y-dimensional vector t. So it's a very straightforward mathematical computation which shows us that using these random features, we can approximate the energy with only a single vector. And this is what we call the distributed representation dense associative memory. Whereas the original version where we have to keep all the memories is what we call the memory representation, dense associative memories. So this is a very simple application of the powerful result shown by Rahimi and Recht, and kind of that this is kind of what we study in our paper, and this video kind of visualizes like the same calculations I just showed, but for a very specific kernel. So you're considering over here the radial basis function kernel, and this is just showing a very specific set of random features that have been developed for the RBF kernel, where essentially you sample vectors from an isotropic Gaussian in the d-dimensional space, and then you apply trigonometric functions to it, so cosine and sine to it, and then do that for y different random features, and that gives you an explicit representation of your input, this phi. And so given these random features, what has been shown that if you have the number of random features you have is of the order of d by epsilon square, then these approximation in the kernel values is bounded with high probability by epsilon. So we want epsilon to be pretty small for things to work. That means y needs to be fairly large, significantly larger than d, and ideally we want it to be as large as we can make it computationally. So starting from the energy of the memory representation, we arrive at an approximate energy using the distributed representation. And if you think about in terms of the number of parameters, we have now gone from m times d parameters that we have to keep around to O of d by epsilon square. Again, whether this is an improvement or not will depend on how big or small epsilon is. But you can see that we are, again, able to disentangle the number of parameters that we want to save in our model from the actual number of memories, m. So this value no longer depends on m, and then it's kind of, we can make m as large or small, but this number will stay the same. Of course, if we are in the regime where m is polynomially large or exponentially large, then this could be an improvement over the memory representation. So it depends on the application. It depends on where we are using this approximation. Now, once we have to accept that this is an approximation, so nothing is free. So it's not going to be universally working everywhere. So we wanted to quantify where this approximation works and where it will not work as well. And so to quantify the approximation, what we considered is kind of the energy descent. We wanted to quantify the divergence in the energy descent. And so if you have the true energy using the memory representation, then this would be our model output, and thus using one-step energy descent. And using the approximate energy, this would be our model output using the approximate energy gradient. And we want to quantify that if we do the iterative energy descent with these two different energies, how far do we get, how far can we diverge? And what we can show is the specific result, but I'll walk through this step by step. So the left-hand side, which is what we are trying to bound, which is the approximation, in t-step energy descent. So we are taking different t steps in the energy descent using the appropriate energy gradients. And this quantity is bounded, of course, like a major factor is this square root of d by y. This is tied to the quality of the random features, as I had mentioned, that y needs to be d by epsilon square. So if you invert that relationship, this term square root of d by y shows up. So if my dimensionality of my individual memories is large, y needs to grow correspondingly to keep the approximation low. And for a fixed d, if we grow y, then approximation will progressively get better. Another factor, this constant C1 actually is tied to the qualities of the random features themselves. And as I said, like initial set of random features that were proposed by Rahimi and Recht were pretty powerful, but there were limitations, and better random features have been developed over the last decade, and this quantity kind of incorporates that. If you have a better this dependence on square root of d over y will always stay, but you can improve kind of this constants in front of it, and this incorporates that. The second quantity here, C2, actually depends on the step size for the energy descent. As you can see, like in both the energy descent, we use this step size alpha. And then we are considering the setup where both the energies, the approximate and the exact energy, are using the same step size. And if the step size is small enough, again, depending on the number of steps we are taking, then this term will also be small, and thus the bound will also be small. So it kind of says that if your step sizes are small, then the approximation will be better. But beyond these quantities, another quantity that plays a big role is the initial energy of the input. And this is kind of tied to whether this input is close to one of the memories or kind of somewhat close to one of the memories in my model, or is it far away from all the memories? So it's pretty far away from everything else, which would imply that it will have really high initial energy. But if it's somewhat close to at least one of the memories, then its initial energy can be bounded to be not super high. And then this plays an important role in the approximation guarantees. So this is saying that if I have an input which is far away from all the memories, then my approximation will be pretty bad. But if it has a pretty low energy initially, then this approximation will be much tighter, and then there will be very little difference between the exact energy descent and the approximate energy descent. And we verify this behavior empirically. So we take some random patterns, and we kind of look at the difference between what the exact energy descent gives us and what the approximate energy descent gives us. And the y-axis, or the horizontal axis, is y, the number of random features we use, and the vertical axis is the approximation error. And then each of the rows corresponds to a different dimensionality of the memory vectors. And each of the columns correspond to a different region of the input. So whether they're in a high energy region or a low energy region. So if you look at the leftmost column, you can see the behavior that tracks our theoretical results. So as you increase the number of random features for any given input dimensionality, your approximation improves as expected. And as you increase the dimensionality itself, the approximation is worse. Now, and the leftmost column is essentially looking at inputs that begin at very close to the stored pattern. So they already have very, very low energy. So that's the most favorable case. And in that scenario, our bounds, which are shown by the solid line, pretty much overlap with the actual measurements, which are the circles. So our bounds are pretty tight in that region. The middle column shows the uh, same setup, but here we are a little bit far away from one of the stored patterns. So our energy is kind of not super high, but not super low either. So it's somewhere in the middle. And this is where our bounds uh, are 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 slightly loose, but still not super loose. And we can see the same effect, like as you increase the number of random features, you can see that the approximation improves. As you increase the dimensionality, the approximation is affected adversely. Um, and finally, on the rightmost column, we are working with inputs which can have really high energy. And in that case, you can see that sometimes our actual performance as well as our uh, bounds can become much more looser. And in some cases, for example, in uh, the bottom two plots of the rightmost column, you can see that in certain scenarios, our retrieval errors are pretty bad, and we cannot effectively retrieve the original memory. So we have again um, like lost those memories. So this
Pari,
qualifies. Yes.
sorry, just one question. The beta parameter, what is that again? I forget now.
Yeah, so I thank you for bringing this up. This is something that I should have explained better, but it's essentially um, uh, it's often known as the inverse temperature, and it also drives
Okay. Mhm. Yeah.
how quickly or how slowly your similarity grows. So it's a linear scaling of the similarity, and the larger you make it, the faster your kernel value, for example, will grow here, and which also corresponds to higher beta. Usually corresponds to uh, how quickly your energy grows as you move away from the stored patterns. Um,
And
and
how is beta defined in the framework of random Fourier features? So it's not temperature, right? Like in the standard Hopfield model.
I mean, again, the again, maybe I should go back here. If you look at this equation, we did not include a beta parameter here, but the beta parameter would be what would be in the numerator of the half. So right now you have exponentiation of negative half of the Euclidean distance between the x and the memory.
Mhm.
But instead you would have a beta. It would be
Okay, okay.
negative beta by 2.
I see.
And and
Mm.
one of the things you can do is you can incorporate the beta as in the vectors themselves. So you can replace
Yeah, yeah, yeah. Mhm.
as square root of like
I
square root
see.
of beta inside of it, and then
Mm.
you can apply everything with beta. You can imagine beta equals 1.
I
Um,
see. So it kind of defines the width of the Gaussian that you use here.
yes, yes, yes. So
Okay.
there is a correspondence there.
Yeah.
Yes.
Okay.
Um, and yeah, and I think somebody made a comment that this is kind of related to the resolution to some extent, yes, and that is true. Uh,
I, Ari, I have a very quick question on this graphs you show here. What was the size of memory? I mean, number of patterns uh, in this setup? M.
oh, M. I think we had about 1,000. M was around 1,000 here.
Hmm. Okay.
Yeah, I should have added it on the figure. Apologies. Um, yeah. Yeah, M was about 1,000. But in our if you look into our paper, we tried different values of M and different values of like we cycle through different values to see how that affects our performance.
And so for the smaller t's, you could almost, oh no, yeah, I see. So 1,000, I see. Yeah, so you're always above the standard Hopfield capacity here, even for t equals 1,000. Yeah.
Yeah, I mean, because it's like 0.2 something, right?
0.14, yeah.
Oh, 0.14, yeah.
Yeah.
So again, as I said, like the approximation varies, like depends on many different factors. And there's also an relationship between the number of memories that you put in and what your beta value should be. If you have a lot more memory, you probably want your beta to be large so that you can disambiguate between different memories. So you have higher resolution, and that implies and higher beta implies anything that's not close to one of the memories can have high energy. But if you're packing in many energy, your chances of being close to at least one of them kind of goes up. So there is this uh, weird trade-off, which again is tied to this um, sorry this result that we have where um, um, you have a dependence on the initial energy and the beta. And if you want to make beta large, it has both. It can hurt you, but it can also, if beta is somehow tied to the number of memories you have, then the effect is kind of the number of memories itself starts factoring into this term. Right now, it doesn't factor into the term at all. Or it does not factor into the term explicitly, but if beta depends on m somehow, which can happen, then it would also play a role here in these bounds. And beyond quantitative results, we also wanted to show some qualitative results. So the top row is essentially like, again, corrupting a memory that we had stored. And the middle row is the memory that we retrieved from our distributed representation of the energy, the approximate energy. And the bottom row is where we did not approximate the energy. We used the actual energy, all the actual memories. And then these are the retrieval patterns. And you can see that the middle row, which is the approximate energy, does have a little bit more noisy retrievals, but it in most cases it keeps the shape. It's able to recover the shape of the original memory. Even like intricate patterns like the legs on this shrimp, you can see that it still recovers it, but there's a lot of noise in the background, some noise in the background. But these are just qualitative results. And this is kind of like there's a lot more results, both qualitative and quantitative, of studying the effect of all these different factors. And it was part of our paper, dense sensitive memories through the lens of random features. And again, can get to the actual paper through this QR code. And I know like this is a VSA online VSA forum, so I do wanted to spend some time kind of talking about connections to VSAs. And as I mentioned, like we can think about like the model, like having some memories. Like I have m memories in some d-dimensional space, and in associative memories, we think of them as memories, and this distributed representation using random features that you compute in this form has an interesting property. And this is the property, right? That at each memory, there's a high similarity or dot product between this distributed representation and the memory. So that's why these memories can form local energy minima. But if you pick any random input, it will probably have low similarity and thus have potentially higher initial energy. So kind of this is a property of this distributed representation. Now, there are some parallels of this in VSA architecture, VSAs, which again, I'm not an expert, but I know a little bit about it. And one of the things is what I understood was that we often represent items as hyperdimensional vectors. So if we imagine that these M vectors are hyperdimensional vectors, where D is really large and the vectors were drawn from the specific architectural distribution, then there's a distributed representation which can also be created for these items by bundling them. So you bundle these hyperdimensional vectors, and this bundle also has has a desired property, right? The desired property is that each item in the bundle has a high similarity to this distributed representation, but any random hyperdimensional vector probably should have low similarity with this bundle vector. And kind of this bundle of hyperdimensional vectors have similar properties to our distributed representation of the memories. So this is one parallel I kind of wanted to just draw between what's there in the associative memory world and what I kind of understand of VSAs. Another connection is retrieval. And like I know like in dense associative memories, retrieval is a very important concept, but so it is in VSAs. But in associative memories, retrieval is kind of done via this iterative energy descent process, right? Like we have an energy and we take a gradient of this energy, and it's almost like a more continuous process. Whereas again, to the best of my knowledge, in VSAs, the retrieval is often via the single shot similarity search. So like VSAs come with their own notion of similarity, and then so the output for any similarity search is usually like finding for any particular input, which is a hyperdimensional vector itself, the other hyperdimensional vector which has a high similarity to it. And this is a single shot process, and often like so you can think of it as a discrete process. So that's kind of one like I don't know if there is a connection. There's a more better counterpart of the continuous process that's in associative memories in VSAs. I'm not aware of it, but doesn't mean it's not there. But this is kind of like the target is the same, but the process is slightly different in these two worlds, to the best of my understanding. And with that, I want to thank you for your time and for this great opportunity. I mean, this is one paper that we discussed, but we have been working with Dmitry Krotov and many of our collaborators and trying to make other connections between these associative memories and just more traditional machine learning problems. And we have some papers here. If you're interested in that line of work, feel free to check out our work. And with that, I thank you for your time.
Pari, thank you very much for the great talk. So now I open the floor for questions. So Fritz, you.
Yes, Pari, thanks. Yeah, very interesting work. I have one question. So basically how you store the random Fourier features of the patterns in your model is just by adding them up into a vector. Have you also explored actually to store the outer products, like in the standard Hopfield model, to store actually the outer products of these vectors into a matrix and then use a standard Hopfield network to retrieve? That should probably also work, right?
A minor distinction. So actually, these are both equivalent. So what you just described are equivalent, except there's a minor difference where, let me see if I can show this.
Because you kind of optimize the inner product between the input encoding vector and of the distorted pattern, right? And the T vector, right?
Yeah. So what will happen is if you write it out, So this would be more like the standard Hopfill network that you're talking
Exactly.
about.
So yeah.
Mm.
So it kind of it minimizes the square of the inner products, right?
Right, right. So what you need in this setup is in the more general setup where you use these random features, it would be an outer product of the memory with the random feature of the memory, not the outer product of the random features themselves, but the outer product. So it would be like psi mu times phi of psi mu transpose. And then if you write it out, if you write your T matrix like that, and then you replace these V's with the phi of V, then that becomes precisely like you're kind of doing standard Hopfill network,
Mhm.
but
Just in the feature space, basically.
yes, yes. So there is but they are equivalent. And since they're equivalent, we wanted to reduce the model size. Otherwise, we would have to store a Y by D matrix instead of just a Y vector. So to get
Yeah.
around that, we just stored a Y vector, and that is the reason. But otherwise, what you said is absolutely correct. It would be equivalent.
Well, I'm asking because if you think of patterns maybe where your Fourier features are used sparsely, right? Then you actually can have an advantage of using the outer product matrix because then you can actually store order of d squared patterns, right? So there are these old results of sparse associative memories where actually the memory capacity is not O of d, but is close to O of d squared. And I'm
Yeah, no, that is
wondering if,
possible. So that
yeah,
is an open question, though. So what you raised is an excellent point. What I'm not aware of is random features being sparse. That's actually an active line of research where people have been trying to find random features which approximate the kernel value and are still sparse. And there isn't. And usually these random features tend to be extremely dense.
yeah,
But if they
okay.
are sparse, what you're saying is correct. Like the outer product might be
Yeah,
uh, very sparse, and thus the amount you need to store can be
large.
lowered.
Yeah,
Okay. No,
thanks.
that's an excellent
Yeah,
point. Thank you for your questions. And
Pari, maybe quickly, I want to return back to my question about the size of memory. I mean, number of items in your memory in your
yeah,
experiments. I very quickly, I probably should read it more thoroughly, but very quickly scanned that paper, but I couldn't find some exact references to number of items you used in the experiment. But let's put it simple. What was the largest number of items you experimented with? Like you mentioned 100, but I mean the
um,
largest number.
yeah. I think we went up for the quantitative results, not involving images. We went up to 1,000, or I think we were trying to ablate the effect of different quantities, and we did go up to like 100 or like 1,000, depending on what D is. So we would vary on that.
Yeah,
But we did
because
not go up to the exponential size,
yeah,
if that's what you're.
what I'm thinking and why I'm asking this is that I mean when you go into this um, dot product, I mean the expression of T as dot product of sum of random features. I mean on the next slide, right?
Uh,
It-
this one?
yes, yeah. Um, so basically. So here you sum over the number of items you stored, I mean the random
Yeah,
features. And to me, so I mean, as you yourself made parallels, so that's similar to a bundle of vectors. And then, of course, I mean, for a given dimensionality of the vector, so I mean, it has certain capacity in terms of number of items it can store. I
yeah,
mean, so basically, my point is that so you kind of prove the equivalence, I mean, not the equivalence, but the expected, the approximation depending on the D. I mean, and um, but maybe. I just wonder if M should also be taken into account for defining the Y dimensionality of Y of random features.
Yeah, that's a good question. So usually what happens is that this bound for Y comes from
This
just
I
like
understand. This I understand. So that's kind of nature of random features. But what I
yeah.
mean is that I mean on these dimensionalities that you I mean that you showed on the graphs, like 40K, 400K. I mean the capacity of the bundle is rather high. So
Hmm.
so basically, I mean, but if you add, I don't know, 100,000 items to this
Hmm.
bundle, then basically, I mean, the dot product, I mean, you inevitably it will make errors. I
Yeah.
mean, as the number of as the M grows, I don't know if I'm thinking in the right
No, no,
direction.
you're correct. So again, it'll depend on a few factors. So as I was saying on this case, right? So if and this is something that we are yet to qualify.
Mm,
We haven't been because we don't know how beta should vary by M, right? So
mm,
beta kind of should vary kind of some, it's like M to the power negative D. Again, I'm making some stuff up. If
mm,
that's the case, then M will start playing a role. And it's understood that as you increase the number of memories, you need to make your beta smaller for them to be separable.
mm,
Oh, sorry, beta larger for them to be separable. So that is kind of a well understood because otherwise, like you as you said, it's the bandwidth of the Gaussian, right? And for the Gaussian to be able to make two different bow like basins of attraction, the beta needs to be larger. And so if I bring in that dependence on M into this equation, you're absolutely right. Then the approximation will uh, be affected by M.
mm.
And if we say that it is like something of this sort, then like beta is grows with like beta is proportional to M, then this is showing that also our approximation gets worse by M because beta is inside this exponential here divided by just a normal beta. So you're right in that respect. It will get worse.
Okay, thank you. So Paxson, you were next.
Hey, well, okay, so we of course looked at something similar, and I don't know if you're aware of our paper about the fractional power encoding, and but basically, I wanted to ask you a little bit about if you've thought about like a line attractor, or instead of the memories being these points at a local minimum. One of the things we kind of realized when we were messing around with these random Fourier features is that you can pretty easily like make the landscape a line attractor instead of a point attractor. And so I'm just wondering if you've come across that or thought about that.
So that is something that I would love to look at your paper, so I will definitely look up your work. And if you have the specific name of the paper, I would love for you to share it if be possible on the chat. We have thought about it in terms of like, as you said, like we have memories which are points and we want them to be attractors. But what if we could create manifolds that are attractors? And you said like a line is one specific manifold, and that is very desirable. And that is kind of because then with finite memories, we literally are we are kind of learning the manifold, and we can then energy descent from anywhere off the manifold brings us back to the manifold and kind of can give us some new points in the manifold. So it's absolutely um, an important topic. We don't have any good results on it yet. We are still trying to understand what's happening there and how it might be possible. But I don't have a good answer.
Actually, we have a manuscript exactly on that topic. I I should be able to share this with you in a few weeks. We are just finalizing it and putting it up on archive.
That's
Cool.
amazing. Thank you. I see a couple of things that Kenny you posted. Thank you.
Yeah, those
Uh,
are
I will make note of these as soon as I can.
So I think on this note, I want to add that I think there are more parallels than just, I mean, these basic operations, I mean, to your work, so which worth exploring.
Yeah, no, I mean, as I said, like I'm really thank you for giving us this opportunity to come come speak and share our work here. This is this, at least to me, this is an interesting there might be some interesting connections and it would be worthwhile pursuing. In fact, before this meeting, I was quickly trying to search, like, does anybody have any papers that connect VSAs to dense associative memories explicitly? And at least for me, nothing quickly popped up, but maybe, in fact, if somebody here has material that would that covers that, that would be also very, very
But
informational and
I
useful for me.
think even Paxson, what is it, TPAM, it's very closely related.
well, yeah. I mean, we've done stuff with associative memories and with VSAs, and yeah, I mean, exactly like thought about well, because we kind of in this computing on functions paper, we like sort of rediscovered Rahimi and Rect like through VSA, and but then I think, yeah, I guess, like, I mean, it's been something in like that's been in the background. We haven't like published it, but then if you take these uh, Fourier vectors and you start plugging them into attractor networks, yeah, you start to get these funky things where you can get like entire manifolds that have all the same minimum energy. And I mean, it's not really true, and like it's like mathematically true, but then like because of the crosstalk noise, there's like some wobble, but yeah, but it's like kind of something interesting that we've been thinking about.
I mean, and as I said, I would love to learn about this. Again, I realize I did not put my email on here, so I'm going to write it down here. This is should be this is my shortest email that I have, and and I would love to, if possible. I know, like, it's always extra work to send out emails, but if it's possible to share all this work, I would love to learn about it. And I'll definitely look at this paper that you shared. I see two papers here, and I'll definitely take a look at them. Thank you so much.
We have another question, Adam.
It was about the slide we just came from. Apologies, but the on the approximation, like I would really what I'm really interested in is the probability of arriving at the same fixed point, right? Which is I feel like a different question from what kind of bounds can we have on the distance between where we land. Does that make sense?
Yeah. No, so you're talking about uh like you're talking about the event that two things converge at the same point, so they have the same
right.
and these two
I expect this distance to be like I expect all bounds to be relatively weak because of if you have a relatively chaotic dynamical system, which you can recognize in this formula. But then it would be interesting to see, like, statistically speaking, how similar are these processes of converging to a point in the space.
Right. Hey, yeah. I mean, we didn't do an analysis of that sort, but that is something definitely. I think it would be honestly a little bit harder to analyze, and then we went with just more of a divergence analysis. But I think that this is also important to do, uh, and then related to that, it would also kind of talk about the capacity of this system. It's not going to have the same capacity because there are going to be memories which are going to be lost here, and then we are yet to characterize that in this system.
Mm-hmm. Yeah, definitely. That's I can see that future. I don't think that getting the probabilities would be that much harder than this analysis on the basis of that you're basically integrating over the divergence, right? So if you have a length of a path to get to there, then you integrate over the sampling procedure on each point of the path, which you already have, you already have the shape of what this looks like by analyzing what a gradient looks like.
Yeah, no, that's true. That's a great point. Yeah, thank you.
All right,
thank
so
you.
we have time for the last question, maybe. So I see we're close to the end. Any more questions? So let's see.
I mean, one more comment.
Sorry, Fritz.
I'm sorry.
Yeah, somehow yeah. If you can go back to the first question, which I feel you somehow answered with your graphs, but I mean, anyways. So the question is about where the network will converge if it starts with the random pattern. So basically,
yeah. So this is related to this question. I think popped up when I was just describing standard dense associative memories, not this random feature version. And I think for that it depends on like many different factors, but usually it would be whatever your closest memory is in that space. If it's random, but whatever your closest if the memory is configured appropriately, the system is configured appropriately, it'll just end up at its closest pattern, even if it's very far away.
Yeah, thank you. Fritz, please.
Yeah, just one more comment to this connection between VSAs and associative memory. Of course, Pari, in VSAs, there's always implicitly, it's often not even described, but this cleanup procedure is actually also a content addressed associative memory. So basically, in almost all VSA computations, you do have actually an associative memory process involved too.
Yeah, no, that's a great connection. Again, as I said, my connections are very limited. Yeah, I think, and in a way, the cleanup process, at least for some of them, if I understand correctly, they have to be brought back to the form that the original vectors have. So if it's a sparse version, they need to be made sparse of the same level.
Well, it's more like a lot of the operations in the VSA chain of operations is lossy. For example, if you do an unbinding, then often you get the right result plus noise, and the noise is really not small. So the only way to get rid of that noise is actually to do a content addressable, to run a content addressable associative memory with all the atoms that you used stored as the fixed points, so that you actually get then to the noise-free answer.
Okay. Yeah. My understanding was usually it would just be a kind of a similarity search, but you're saying there's actually an
energy. It is, yeah. It is a similarity search. That's right.
Okay. Yeah. Okay. You're right then. That's right. Yeah. Thank you. Thank you for the comment.
Okay, and I think on this positive note, let's end this webinar. So I think it was really great seminar and discussion. So thank you all for attending. Special thanks to Pari for presenting this great work. So I hope to see you more often on our venues.
Thank you.
Yeah, thank you all. See you in 2 weeks from now.
Thanks for organizing.
Thank you.
Thanks for hosting me.
Goodbye.
Thank you all for your time. Bye.
Bye.